Welcome to today's paper reading. Today's paper is titled, Chameleon, a data-efficient generalist for dense visual prediction in the wild. This paper was published on AR14 by Donggyun Kim and colleagues from KAIST and Microsoft Research Asia. The abstract introduces a universal model designed to adapt flexibly to unseen dense label structures with minimal data. This model serves as a data-efficient vision generalist, built upon a powerful meta-learning framework. It addresses the challenge of generalization in low-data regimes across various real-world tasks. The model is evaluated in diverse scenarios requiring low-shot learning, demonstrating its ability to adapt with as few as 50 labeled images, outperforming existing approaches. Figure 1 introduces Chameleon, a data-efficient generalist capable of adapting to various unseen dense visual prediction tasks in diverse real-world scenarios. Chameleon can handle tasks with arbitrary output structures using just a few examples, typically dozens. Additionally, it has the capability to learn and utilize multimodal inputs and user interactions, enhancing its versatility and applicability in complex environments. Generalist models are designed to handle a wide variety of tasks with less supervision, primarily through a universal learning framework and large-scale pre-training. However, these models face significant challenges when applied to dense visual prediction tasks, which involve high-dimensional outputs with diverse structures and semantics. Existing methods often struggle with out-of-distribution tasks that have unseen output structures and semantics. To address these challenges, the authors propose a method based on visual token matching, VTM, which includes a task-adaptive feature reweighting module and meta-training on a diverse dataset to enhance generalization capabilities. Figure 2 illustrates the difficulties faced by existing generalist models when attempting to learn out-of-distribution tasks that involve unseen label semantics, such as 6D pose estimation, or unseen label structures, like animal keypoint detection. These tasks are particularly challenging because they require the model to adapt to new and complex output formats that were not encountered during training. The figure highlights that while in-context learning, ICL, and prompt tuning, PT, are used to facilitate adaptation, these methods are not sufficient to overcome the inherent limitations of the models in handling such diverse and novel tasks. This underscores the need for more flexible and robust adaptation mechanisms in data-efficient vision generalists to effectively address a wide range of real-world problems. Generalist models in computer vision primarily use multitask learning, which trains a unified architecture to handle diverse tasks. However, this approach necessitates a substantial amount of labeled data for each task and struggles with generalization to new tasks. In-context learning methods aim to address unseen tasks but are limited to in-distribution tasks or focus primarily on segmentation. Few-shot learning, on the other hand, focuses on learning from a minimal number of labeled examples. It employs specific architectures for tasks like image classification, object detection, and semantic segmentation, but these are not suitable for out-of-distribution generalization. Chameleon is designed as a versatile model capable of learning arbitrary dense prediction tasks with minimal labeled data. The model generates per-pixel labels adaptively based on a small number of labeled examples. The overall framework employs a token-level matching problem between query and support images, incorporating task-specific parameters for adaptation. The encoder design is based on a transformer mechanism, allowing flexible handling of multimodal inputs and task-adaptive feature reweighting to adapt to various tasks with unseen semantics and structures of labels. Figure 3 illustrates the encoding mechanism of the image encoder designed to handle multiple input images. The mechanism is based on a transformer architecture, which allows for the contextualization of token embeddings across various modalities. A key feature is the use of a learnable positional embedding that extends relative position bias, enabling the model to incorporate varying relationships between input modalities and spatial priors adaptively per task. This hybrid position bias ensures that the encoder not only handles different numbers of positions, but also adapts to contextualize distinct relationships between modalities of each task separately. Figure 4 illustrates the task-adaptive feature reweighting mechanism within a hierarchical architecture. The focus is on the matching module situated at the third level of the hierarchy, denoted as L equals 3. This mechanism employs a learnable matrix lambda-t to reweight the multi-level image features, ensuring that each row of lambda-t is normalized to sum to 1, maintaining a constant total contribution from the image feature levels. This approach allows the model to adaptively relate different levels of image and label features based on each specific task, enhancing the model's ability to capture arbitrary correspondences between these features. Figure 5 provides a comprehensive summary of our meta-training dataset. On the left side, the outer circle represents various image domains, while the inner circle indicates the source datasets contributing to these domains. The size of each segment corresponds to the dataset size, offering a visual representation of the data volume from each source. On the right side, the inner circle categorizes the tasks, and the outer circle details the specific tasks within these categories. The size of each segment here corresponds to the sampling ratio, illustrating the distribution of tasks within the dataset. This dataset, composed of around 1.2 million images from 6 prominent datasets, covers a wide range of domains and tasks, making it generally applicable to many real-world scenarios. Figure 12 illustrates the learned feature weights in various downstream tasks. The feature weights are shown to vary substantially across different tasks, indicating the model's ability to adapt its matching modules to tasks that are out of distribution. This adaptability is crucial for the model's generalization capabilities to unseen tasks. The figure highlights the effectiveness of the feature reweighting mechanism in improving performance, especially in tasks where the structure and semantics of the labels differ significantly from those in the meta-training tasks. To enhance the generalization of Chameleon in dense prediction tasks, the authors have taken two main approaches. Firstly, they have curated a large-scale meta-training dataset consisting of around 1.2 million images from 6 prominent datasets, covering 14 different dense prediction tasks. This diverse dataset ensures that Chameleon can be applied to a wide range of real-world scenarios. Secondly, the model's capacity has been scaled up by using a pre-trained BITV2 large image encoder and a VIT large label encoder, with increased dimensions and heads in the matching module. Additionally, the number of convolution channels in the label decoder has been increased from 96 to 256. To address the sensitivity of dense prediction performance to image resolution, Chameleon adapts to the resolution defined for each target task through spatial interpolation of positional embeddings. The model is initially meta-trained at a resolution of 224 by 224 and then fine-tuned at the adapted resolution, which significantly boosts downstream performance. The evaluation of Chameleon was conducted on 6 benchmark datasets, AP10K, LineMod, and ISIC 2018. These datasets were chosen to test the model's adaptability across various tasks. The evaluation metrics used include mean average precision, AP, ADD score, and average F1 score. The performance of Chameleon was compared against both generalist approaches and specialist models. The results demonstrate significant performance gains, highlighting the effectiveness of Chameleon in low-shot learning scenarios. Figure 6 presents the qualitative results of Chameleon in 6 downstream benchmarks. The outputs from different channels are color-coded for clarity. The variable T denotes the frame number, indicating the temporal progression in the benchmarks. This figure showcases Chameleon's performance across various tasks, highlighting its adaptability and effectiveness in diverse visual prediction scenarios. Figure 7 illustrates the keypoint prediction capabilities of Chameleon on 8 different animal species. The model successfully predicts keypoints across species with varying appearances and body configurations. Notably, Chameleon utilizes spatial priors to accurately localize missing parts, such as occlusions in antelope and cat, and effectively distinguishes between left and right body parts. This demonstrates the model's adaptability and effectiveness in handling diverse and complex visual prediction tasks. Figure 8 illustrates the attention maps generated during the 6D pose estimation process. The visualization focuses on the interaction between a query image patch, highlighted by a red box, and the support patches across different output channels. Chameleon, the model in use, effectively captures the 3D spatial relationship between the query and support by directing attention to the back, left, and bottom parts of the object for the X, Y, and Z channels, respectively. This approach demonstrates a high correlation between the similarity scores of the query and support images and their corresponding 3D positions, which is crucial for accurate 6D pose estimation. Figure 9 presents a qualitative comparison between various generalist models and their ability to predict medical semantic segmentation tasks out of domain. This comparison highlights the adaptability and performance of different models when faced with a significant domain shift, such as transitioning from natural images to medical images. The visual representation allows for an intuitive understanding of how each model handles the complexity and specificity required for accurate medical image segmentation. This analysis is crucial for evaluating the robustness and generalizability of machine learning models in real-world, domain-specific applications. Figure 10 presents the video segmentation results using 1 and 2 support frames, indicated by red boxes. The study highlights that while Chameleon successfully tracks objects under significant appearance variations, most failure cases of the method are attributed to ambiguous distractors. These issues can be mitigated by incorporating additional frame labels, which is a feature that Chameleon can naturally integrate. This capability allows Chameleon to surpass specialist methods when provided with 4 frame labels, as illustrated in Figure 13. Figure 13 illustrates the downstream performance of Chameleon, a data-efficient generalist model, as the size of the support set varies. The blue line indicates Chameleon's performance, which consistently improves with an increasing number of support labels. Notably, Chameleon outperforms specialist models across various benchmarks when provided with as few as dozens of labels. The dotted lines in the figure correspond to the performance metrics of these specialist models, highlighting Chameleon's superior generalization capability in dense visual prediction tasks. Figure 11 illustrates the effectiveness of using multimodal input in Chameleon. In Part A, the exemplar guide is used to exclude false positives, such as bushes, in object counting tasks. This demonstrates Chameleon's ability to refine counting results by leveraging additional guidance. In Part B, Chameleon successfully separates 2 cells that are entangled in a cytoplasmic image by utilizing information from a nucleic image. This showcases the model's capability to handle and integrate different types of input data for more accurate segmentation. Overall, Figure 11 highlights Chameleon's adaptability to multimodal inputs, which is crucial for tasks with vastly different semantic requirements. Table 1 presents a comprehensive comparison between specialists and generalists in the realm of dense visual prediction tasks. The table highlights the performance metrics across various tasks such as animal keypoint detection, 6D pose estimation, skin lesion segmentation, video object segmentation, object counting, and cell instance segmentation. The generalist models, including Painter, SegGPT, and VTM, are evaluated under different settings of in-context learning and parameter-efficient fine-tuning. Notably, the generalists utilize one-shot support for the Davis 2017 dataset, 20-shot support for AP10K and ISIC 2018, and 50-shot support for other tasks. This comparison underscores the effectiveness of the generalist approach, particularly Chameleon, in low-shot learning scenarios, demonstrating significant performance improvements across diverse tasks. Table 2 presents the results of an ablation study focusing on the contributions of each component to the model's performance. The study starts with the VTM baseline and progressively adds enhancements such as an enlarged backbone, large and diverse data, a variable input encoder, and feature weighting. The performance metrics evaluated include AP50, JNF, MAE, ADD, AP, and F1 across different datasets like AP10K, LineMod, ISIC 2018, Davis 2017, FSC 147, and CellPose. Notably, the addition of feature weighting shows significant improvements, especially in tasks where the structure and semantics of labels differ from meta-training tasks. Table 3 presents an ablation study on the meta-training dataset, focusing on the impact of increasing the scale and diversity of the training data. The study uses Chameleon, a data-efficient generalist model for dense visual prediction tasks. The table shows that as the diversity of domains and tasks in the meta-training dataset increases, the performance of Chameleon consistently improves. Notably, improvements are often observed when adding tasks that are less or barely correlated with the downstream tasks. For example, adding synthetic drone images with continuous labels, midair, significantly enhances animal pose estimation, and adding keypoint detection tasks, KP4, improves 6D pose estimation. This indicates that the model can effectively leverage indirect correlations between meta-training and downstream tasks through universal matching, which is crucial for generalizing to unseen out-of-distribution tasks. Chameleon is a data-efficient generalist designed for arbitrary, unseen dense visual prediction tasks. It is based on a token-level matching framework, which includes a flexible encoding mechanism for multiple input images and a powerful task-specific adaptation mechanism for hierarchical architecture. The model has been tested on a variety of tasks with distinct label structures and semantics, demonstrating its ability to learn effectively with minimal labels. Extensive experiments have validated its performance across diverse tasks. Thank you for watching.